Hey, I'm Thomas Webb. Some of you might recognize me from the forums and stuff. Uh, Last year I did talk about audio programming and hacks as well, but there's been more work that I've done since then, and I just want to share some of that. But hopefully this talk is useful whether or not you saw my talk from last year. And I'm focusing this time primarily on real-time audio programming. Not anything possibly related to audio, because some of the use cases for audio programming are covered, like just the simple stuff, loading an audio file and playing it. There are already ways of doing that in hacks. Here are some other talks that I recommend to get acquainted with audio development. Just in general. So the first one is Why Game Audio is Not a Solved Problem by Guy Somberg. And in general, I recommend his talks and his writings. And he has some interesting books too, like game audio programming. But that's more game audio related, not quite the same thing that I'm talking about. But it should disabuse anyone of the idea that game audio is like a simple thing that is already covered. And then the second one, Real-Time 101, that one I think is very important if you want to get into real-time audio programming. It talks a lot about the pitfalls of that, but I'm going to talk a little bit about some of the points they make in this talk. And then the last one on this list is just my talk from, I think it was last year. So I have that link there, but you could probably Google that, because all these links are like not clickable to you. So what is real-time audio exactly? So to distinguish it from something like that you might do in like a simpler multimedia project, like loading a file and loading an audio file and playing it, or loading a sound effect and playing it, or whatever. It's something where you are filling in audio buffers in real time in a separate thread that is connected with the sound card. So it's a hard real-time requirement. You must finish filling it by a certain time or you'll get glitches. And glitches are really bad. They can actually damage equipment in some cases. But your PC speakers won't be damaged, but it will not sound good. You definitely don't want glitching. The other thing is latency is bad. So if we're making, say, like a synthesizer or anything music related, you don't want to like play a note on your keyboard and then like half a second later hear it. That it needs to respond to that key press right away, at least in terms of human perception. And then also timing matters. So it's not quite the same thing as latency and real time. Like it's another thing to consider. So let's say you fail to fill in the audio buffer in time, then your next audio callback might not be sequential. It might be sometime later. So you definitely don't want to ever fail to do that. But if you do, you don't want that to cause you to drift out of time. So an audio callback that's suitable for real-time audio will also give you timing information, so you know how much time has elapsed since the last audio callback, and you can use that to time things. There are other ways that musicians and producers use to synchronize time, and that's also all important when implementing things for musicians and others to use. And then related to the hard real-time requirement, you optimize for worst case scenario, not average performance. So you could think of like the other side of that spectrum being something like a big data application or bioinformatics or something like that, where you have a lot of data to process and you want the whole process to be as fast as possible. If you don't necessarily care about the worst case scenario. Maybe a few of the pieces of data take longer to process because they're more complicated. But as long as the average and the total are low, that's what you focus on. With audio, real-time audio programming, there's basically a maximum amount of time you ever want to take to go through that audio callback. And you just have to make sure that the worst case scenario is acceptable. So anything that could be unpredictable, you want to avoid, like mallocs and stuff like that, mallocs and freeze. Another point is it's often neglected by non-audio people. So this is something you might hear from like audio, not programmers, but like sound designers working on games. A lot of times they will feel like they're not being well supported by the development team if they don't have like a special audio programmer. And also people who don't really think about audio stuff might underestimate how much of a task it is to get things right and sounding good. And then obvious point, but you're dealing with arrays. So audio, when you're doing audio programming, usually you're doing something to an array of data. It could be floating points or it could be integer types, but you're dealing with arrays of numbers of some sort. And a lot of what I'm saying here applies broadly to anything that's DSP programming, but I'm talking about audio programming. So DSP, digital signal processing, that also applies to like two-dimensional, like image processing. And to be a really good audio programmer, you should also be good at DSP. I would consider myself good at DSP, but I'm trying to learn more. So that's kind of an overview of what real-time audio is. So just to kind of bring that point further, here's like a line from the port audio documentation about the importance of keeping your callback pristine. The port audio stream callback runs at a very high or real-time priority. It is required to consistently meet its time deadlines. Do not allocate memory, access the file system, call library functions, or call other functions from the stream callback that may block or take an unpredictable amount of time to complete. And then here is from, I actually highly recommend reading this whole thing if you want to get into audio programming. It's Real-Time Audio Programming 101, Time Waits for Nothing by Ross Benchina. Ross Benchina is I don't know if I'm pronouncing his name right, but he's a open source audio developer. And if you're into audio development, you probably recognize his name. But here's a quote from that. You don't want your software's audio to glitch, especially if your software is going to be used to perform to a stadium full of fans, or to watch a movie in a home theater, or to listen to a symphony in your car while you're driving down the freeway, or anywhere really. It's so fundamental, I'll say it again. You do not want your audio to glitch, period. And he goes in to make a lot of the same points that the port audio documentation makes about not calling library functions, not using locks, not managing memory. Why? And then next obvious question though is why use HACS for real-time audio? Because probably most of it is done in C++ or C. That's kind of the standard. So this is more of a question that an audio programmer would ask me. Why would you use HACS for it? And here are a couple of reasons why I think HACS is, or at least can be, a good language for it. One is you can reuse your audio code in multiple environments. And for me, environment is a broader concept than just target. Like target refers to the programming language, but there are multiple environments per target. Because one environment could be like standalone application. Another could be a plugin that you load in an application, or a plugin that you load in a game engine, or the difference between JavaScript, HTML versus Node.js. So there's at least a potential to write audio code that can be reused in multiple different environments and even configurations. Hex has awesome features that can can create abstractions that go away after compile time, like abstracts and macros. And you can use that to make your code more reusable too, to transform it as you need it. And while Hex isn't currently a popular language for people to write audio code in, there still are a lot of creatives writing in Hex. In fact, some of them are audio programmers. They just haven't written any audio code in Hex yet. And actually, some of them have, not just me. But not very many people have written real-time audio code in Hex yet. But the fact that there's so many creatives, that's kind of synergistic, and that might be a good reason to want to tap into that community. And then Hex is just a good general purpose programming language. So you do have, in the audio space, I mentioned C++ is widely used. There's also some other things like Faust and Soul is a new thing by the makers of Juice. And those are domain-specific programming languages for audio. But Hex is cool because it's a good general-purpose programming language. And it, in some respects, takes you more places than C++ does. You can definitely get into the browser with C++ now by using WebAssembly or whatever it's called now. But with Hex, you can generate JavaScript, and there's still some advantages to doing that. And the Hex is just a good general-purpose programming language. It has interfaces, it has classes, it has different ways of typing, has an excellent macro system. So I'm preaching a choir now, but later I'm going to make a separate talk that I'll just upload to YouTube for audio programmers, and these will be good points to use then. And why not use Hex for real-time audio? Really, the biggest thing is garbage collection. And oh, by the way, I mentioned the talk I did last year. In that talk, I go into a lot more detail about pros and cons, and most of the points I didn't want to rehash. I decided to focus on just kind of the main ones. But if you want to look at more pros and cons, I go into it more then. And then also, like an old blog post of mine, I talk about it. But the main downside of Hex is for real-time audio is garbage collection, and the most performant of the targets that I focus on is the HXCPP target. And as you saw in the talk earlier by Hugh, he didn't even use Hex for the RS-232 or whatever serial communication because it is real time, and he didn't want to have to deal with garbage collection. So that's the same issue that I run into trying to write audio code in Hex that runs in the audio thread. You're having to deal with garbage collection then, and if the garbage collector runs when you don't expect it to, then you get glitches. So to really make it a suitable language, you have to find some way around that. And I get into some of the ways around that here. One is just to do what he did and not write your real-time code in Hex, but write it in C++, and then have your Hex code communicate with it. That is certainly a possibility. Another reason to not use Hex for real-time audio is also kind of a reason to do it, depending on your personality. But the fact that no one's doing it means that you're not going to be copy-pasting very much. One of the few copy-paste opportunities for real-time audio code is the stuff that I put up on the internet, on the tutorials that I made. So there's not a lot there. There's not, if you want to know how to do this thing in C++, there's lots of stuff on Stack Overflow, lots of books full of examples. The fact that there aren't people doing that in Hex means that you're kind of more on your own in that case. I would think that one of the main use cases for writing audio code in Hex is you already have code in another language, and you see some benefit in porting it to Hex. And that kind of leads to my last point here is there's already so much good audio code out there. And unless you're like a major expert in it, chances are there's already good open source code you can use that does what you're trying to do. There's, Google even is pushing the envelope on using machine learning with audio. They have some cool stuff that you can download and play with. So, why bother making your own original code when there's all this awesome stuff out there? But in practice, if you want to make a synthesizer or even a game middleware, you end up having to make some custom stuff. But just a couple things to consider. And as far as, let's say you're not going to use anything external to HAX, as far as what is already there, just with the HAX compiler without using any third-party HAX libs, you actually already have externs for web MIDI and web audio in JavaScript. The web MIDI only works in Chrome, I believe, or at least only WebKit, but maybe definitely doesn't work in every browser. The web audio stuff does work in every browser. You might need to deal with some naming issues in Safari, but yeah, you have externs there. If you go to like api.hax.org and then search for MIDI, the only hits you get are web MIDI. So it is cool that you have that stuff already. And then Java already has in its virtual machine, it already has audio MIDI stuff built into it, which is cool. So you can access the javax.sound whatever, and that includes audio and MIDI stuff. And it's not listed on api.hax.org, but without linking to any third-party libs, you already have it from HAX because it automatically reads that. That's one of the cool things about the Java target is it kind of automatically generates externs for you. So even though it might not have even been thought about by the HAX developers and it's not even listed on api.hax.org, you have access to all that stuff. So you can already make a synthesizer or DAW in HAX as long as you're using the Java target. And you can already make something similar in JavaScript, again, using the HAX target, but you don't have a common interface for both, not yet anyway, although I'm getting there on the audio side. And then I shouldn't have Flash.media in there. That's not really related to real-time audio, but at least it's an audio-related thing that you will see on api.hax.org, stuff to load files and play them. And that's all that I know of that you get out of the box with HAX. And then here's a point that I'm going to come back to throughout this talk is audio programming is an ecosystem. So even if you only need one type of audio functionality, the existence of other audio functionalities that you don't use is still to your benefit, because the more of an ecosystem there is, the more code there is to potentially copy between different environments, and the more it entices audio developers to write for it. One I think pretty concrete example is, these are all things that are not written in HAX. These screenshots that I have, that really ugly one on the left is 4Wise, which is a popular audio middleware. So if your use case for audio programming is you're making a game and you just want to do some like offline rendering or effects and then play it through the speakers, then it's to your benefit to have like a cool audio middleware. But you're not going to implement an audio middleware in a language that isn't suitable for writing a standalone DAW in, because the authoring tools are basically like that. So even if the game itself is ultimately using OpenAL as its way of talking to the sound card, you probably need another application that talks directly to the sound card that the audio people use to generate content. So that's just one example. And then the other things in this picture are, a DAW, my favorite DAW, Bitwig, which is actually written in Java, and a synthesizer, an open source synthesizer, and then an open source audio player. So the more cool stuff like that we have in HAX, I think the better. Even if some of those things, the audio player and the middleware on the game engine side aren't directly real-time audio programming in the sense that I mean it. So here is the libs that I've been working on, HAX Grig. I actually introduced it last year, but there's been more development on it since then. But basically what it is it's a series of libs that are meant to be fairly lightweight and non-intrusive. Like you shouldn't have to do everything a different way to accommodate using Grig. And you shouldn't have to, you should be able to use as much or as little of it as you want. Partly through HAX's dead code elimination. So if, for example, you use Grig.audio, which has externs for port audio in it, if you're not using its audio callback and you're just using it for some audio algorithms, like you're just using its linear interpolator, ultimately it's not going to compile port audio and it's just going to link in the linear interpolator code for you. So it should be pretty simple. But in addition to relying on that, I also have it split into separate libs. And part of the reason for that is down the road, I want to also release those libs for other targets that HAX targets, so that if there is some useful stuff in it, you could also down the road use it from JavaScript or Python or something. That's the ultimate plan. And also just, I think, kind of splitting it, it kind of makes it clear which functionality you're using. As I might have mentioned before, I was kind of inspired by how HAX Tink does things. It has like a lot of smaller libs that you can use, and you just use whichever one that you need for what you're doing. You don't have to buy into this huge library. And so a big part of it is it's meant to be multi-target, multi-environment. So if it's an audio algorithm, that should just be automatically multi-target by virtue of just being more or less plain HAX code. But if it's something like dealing with I/O, that is something that you do have to make externs for each target. And what I do try to do is provide that for as many targets as possible to make the callback interface as useful as possible. So the idea is you can write audio code and then run that in a browser, or compile and run in a browser, compile and run standalone, and so on. So it's not compile once, run anywhere, it's compile anywhere, write once, compile anywhere. I originally started working on this with the idea that I'd start working on cool things like generative music, and I have actually worked on generative music recently for a client, but not in HAX yet. But I had all these lofty ideas. I'm going to do generative music. I'm going to do cool music theory things. But what I quickly found is that there wasn't even MIDI support in HAX. So I pretty much immediately switched gears to working on providing the basic infrastructure that is needed before it is a suitable environment for audio programmers to target. Can I look at, has anyone asked any questions yet?
Doesn't look like it.
Okay, cool. Okay, and then, so far it's just kind of the focus still is on basic infrastructure stuff, but slowly starting to get into more interesting uses of it. Also, the libraries are designed with an asynchronous interface, and that accommodates JavaScript as well as other targets. And one of the cool things that's around the corner for HAX is sysasync. That's going to be like some there's like the whole sys stuff, like file access and all that, and a lot of it's not implemented in Node.js because Node.js has an asynchronous interface. And how I accommodate that on the Grig end is by having a common interface that is asynchronous and wraps around either Node.js or the regular sys stuff. But the code can get a lot simpler after that stuff gets added to Haxe. So there's going to, pretty soon, I think Haxe is going to be a lot easier to port between other targets and Node.js, and that's going to be really awesome. And then the last point is, so far, no one else has contributed code. Others have helped by opening tickets and stuff and using it, but no one but me has contributed code yet. But it'd be cool if other people were interested in doing that. And then here's a list of some of the parts, some of the individual Haxe libs. So the main three that I'm going to focus on are Grig.audio, Grig.midi, and Grig.osc, or focus on in this talk. And then there are others below that are kind of, there either isn't much there, or it's not mainstream enough, or it's in an early stage of development. So Grig.synth and Grig.pitch have interesting things in them, but there's not much to them yet. Grig.synth does have an FM synth in it, but if you do want to do FM synthesis, I actually would recommend looking at the examples that I made and working from there instead of using my port of libfm synth, because I think the former is simpler and easier to understand. And then Grig.pitch doesn't do much. It just calculates note pitches for you. And then Haxe Music PD, that's just like a Haxe client for the Music PD daemon, which plays, it's like a music player that you can control remotely over a TCP connection. And then HXAL, that is a domain-specific programming language that I'm working on. So it's basically like Haxe syntax, but it's meant to generate audio code. And I'll talk about that more towards the end. But that is very much at the proof of concept stage right now. So for Grig.audio and Grig.midi, here are the environments that are already supported for I/O. Reading and writing MIDI files is pretty much supported on all targets, but the more useful thing, I think, with audio applications is having a audio callback or a MIDI callback. So here are the environments where you can get callbacks. Recently, I rewrote the callback in the CPP target for Grig.midi, and I'm also wrapping up rewriting the audio callback in Grig.audio on the CPP target. Both I felt had too much overhead, and they both had an issue caused by not registering the thread with garbage collection. So I have fixed that. So if you're having issues with either of those with more recent versions of Haxe, Grig.midi is fixed and Grig.audio will be fixed very soon. I also recently, in very short succession, like within like a week or two worth of time, added MIDI callback support to additional targets, to Java and to C#. In the C#, it uses a lib called managed MIDI, which in turn targets a lot of different environments. So there's probably no other way to get MIDI access to more different places with a piece of code than using Grig.midi. The main thing that's not being target that it doesn't cover yet are plugin environments like VST. So that is kind of a big omission. On the audio side, I am currently wrapping up some big changes that I made to the CPP target. And after that, I'm going to work on Java and C# and adding support to game engines. You can see that I have heaps listed. So that's one game engine I did cover, and that also in turn covers OpenFL. If you link to heaps and OpenFL and you use the audio callback, it will play through that engine. But it doesn't have, when you're using the game engine environment, you don't have the full callback support with like the timing information and all that. I'll get more into that in a second. So I'll start by talking about Grig.audio. So Grig.audio provides one interface for audio callbacks. So you can see this code is pretty simple, and it's an asynchronous interface. So it returns a feature, and then you handle it. And then you can see an audio callback. It's not super efficient. It's using like the math.sine to generate a sine wave. And it's just doing that on the left channel. And yeah, that's pretty simple. You write this code, and that's going to work in all those environments listed. And then one thing to keep in mind with audio programming is there are multiple different ways. There's even more than these two, but these are the main two ways that you'll see audio data being laid out. So it could either be an array of an arrays. So each array in the array of arrays is a channel. So if it's like just stereo, you'll get 2 arrays. If it's 5.1, you get 5 arrays, and so on. And a frame would be represented by like the nth index from each one of those arrays. Interleaved is a little different. You have one array, and then it's just laid out channel 1, channel 2, and so on, and then back to the first channel. And I color-coded it so you can see how that works. There are other ways I've seen too. I've also seen it where you have like a single array, but with the channels kind of separated spatially. So like, you know, all of channel 1 and then all of channel 2. That's actually kind of simple to implement. So it has some advantages. But when working with port audio, these are the 2 options that I got, and those are the 2 I focused on implementing. And this shows you the code once again, but a different subtitle, one interface for audio buffers. So if you look at the code on the top, it's grabbing the channel by doing index 0 of the output. So the output is a buffer, and then it's indexing within that channel to add in the sine wave. So this is basically the interface is based on what it would look like if you were working with channels. But even if you're working with interleaved data, it uses the same interface. And I should also point out, this is a feature that I just added, so it's actually not in there yet. It's in the separate branch where my fixes for the C++ callback are. So you might need to wait like a week or 2 before having access to this. But now with those changes, you can work with interleave code or channels using the same interface. So an audio buffer is actually now an abstract over an interface. And it's an abstract, so I have access to the array subscript ability. And yes, that is syntactic sugar, but I think it's important syntactic sugar because one thing that you do a lot with audio programming is port. And it'd be hard to make the case that HAX is a friendlier programming language if people are having to make their code more verbose than their C++ code was. So I want to make sure that you can use an array-based, a subscript-based interface to work with audio data. And then, okay, the next thing I'll talk about is grig.midi. So this lib provides MIDI I/O, as I mentioned before, and also, like I mentioned before, you can use it to read and write MIDI files. MIDI files are, to me, more of a novelty, but there are definite uses for it. The thing that is still very relevant to musicians is MIDI I/O. So if you're not, just in case you're not familiar with MIDI, a lot of times people hear MIDI and they just think about like back in the 90s and the aughts, the cheesy music that would play on GeoCities websites. And yeah, those were MIDI files playing in your browser through your MIDI instrument, possibly software or hardware on your machine. So those were cheesy because, you know, there's no effects on it. The instrument might be kind of subpar. They are kind of written by amateurs, like fans of the original song. Oftentimes the vocal track was simulated using a saxophone sound, which sounded kind of funny. But don't underestimate MIDI. MIDI is actually a very powerful, very useful, very compatible protocol that's been around as long as I have. It started in 1983 using the same protocol your snazzy new digital audio workstation on your computer can talk to a synthesizer from the early 80s. So the way the protocol works is you have MIDI messages, and it's just like a string of like bytes, and each byte has like flags in it. And then there will oftentimes be like a value that's like a 7-bit value in there. And usually a MIDI message is like 2 or 3 bytes. And one of those bytes, 7 of the bits of that byte will be used to represent a range of values between like 0 and 127. So when you turn like a knob on a MIDI controller, it's kind of constrained by that narrow range of values. So there are definitely limitations of MIDI, but because of its wide compatibility and its power, it's still widely used. Musicians get around a lot of the limitations through other proprietary extensions. So, for example, if you're using a digital audio workstation with like a external piece of, if you're using it with like a an audio plugin, like a software synthesizer or an effect, it'll send like the notes to it as MIDI, but it will change the parameters using a proprietary protocol, like the like VST's parameter automation protocol. So those protocols are more high resolution, so you can change like the value of a floating point data over time. So it's not as constrained as MIDI. But as for like note on and note off, that's pretty, you don't need that much resolution for that anyway. So MIDI still ends up being very, very widely used. And because it is a communication protocol, technically there's nothing stopping you from using it for a non-music application, or also something in between. You can use it to like control lights or something as part of the music performance. And there's been a lot of people doing stuff like that over the years. So it's important to implement MIDI, I think. So, and then here are just some pictures to kind of bring home what I was saying. So like on the far left those are DIN plugs that you use, you know, to communicate between like 2 hardware synthesizers. So you don't need a laptop or anything to use MIDI. You can have like a modern MIDI controller and like an old sound module and talk to the 2 via the MIDI DIN plugs that you see on the left. On the right, you see a more modern USB-based MIDI controller. A lot of times when people think of MIDI controllers, they just think of music instruments or probably even just keyboards, but there's a lot more than that it can be. This right here is used for mixing. So there's a lot of people using MIDI as a way to transmit like volume change messages and parameter change messages and stuff like that. And then some of like the awesome controllers that you use with DAWs these days use MIDI both ways, and the MIDI talks back to it to tell it to like turn on this light or turn on that light. So it's pretty cool in that way. So it's not just about note on, note off. And then in the middle, that shows how MIDI isn't just about hardware, of course. This is software talking to software. So you can have like a MIDI player talk to a MIDI synth. No hardware needs to be involved. Although the funny thing is this particular GUI uses a symbol of a DIN plug looking at it head on to represent the MIDI ports. Because we all associate those plugs with MIDI. At least musicians do. And then, so Grig.MIDI, just like Grig.audio, you get like a single interface for callback. So this is a simple opening MIDI port. This is just opening like the first one, basically, that it encounters. This code will fail if you have no MIDI connected to your system. Grig does support virtual ports, so you do open virtual port, and then if your lib supports it, if your OS or whatever supports it, then it'll open a virtual MIDI port. But in this case, it's opening the first hardware MIDI port it finds, and then it listens in and then prints out the type of the message that it gets. And this is just from the example in the Git repo. So yeah, very easy to write something that works with MIDI. And then if you look in the Grig repo, that has examples that use multiple different things. So in there you can see examples of using both Grig.audio and Grig.MIDI to make synthesizers. So you have like a thread for each. And I think I mentioned this before with Grig.audio. When you talk to a sound card, you get a new thread just for the audio callback. It's the same thing with MIDI. When you talk to MIDI, there's a separate thread that just deals with the MIDI. So that is one thing to keep in mind when you work with this stuff is you could be dealing with like 3 different threads, and you have to make sure to synchronize them and somehow synchronize them without blocking on the audio thread. Okay, and then next I'll talk about OSC. This is something that I implemented fairly recently. This is actually, at one point I thought of this as a pie in the sky thing, and I think I was kind of overestimating how much work it was to implement OSC. Turned out to be not that bad. It only took me like half a month or so. So what is OSC, if you're not familiar with it? OSC stands for Open Sound Control. So OSC is one of the many attempts out there to create a successor to MIDI, saying that does what MIDI did. Another thing, I tend to interrupt myself, but one thing I should mention about MIDI is there is a MIDI 2, and it's finally starting to be implemented, so that gets around some of the limitations of MIDI. Anyway, I digress. OSC is a much more flexible protocol that was made with the idea that this is going to replace MIDI. And while that didn't happen, it's still a good protocol for a number of reasons. It's first of all, it's just an off-the-shelf protocol that you can use, and there's already stuff that uses it. So you don't have to like reinvent the wheel. You can just use OSC if you need some way of having different applications talk to each other. So OSC is address-based. The way MIDI deals with like separating different instruments or whatever are channels. So with MIDI, you get like 16 channels, I believe. So one of the so part of the message defines which channel that it's broadcasting on. So that gives you like 16 different options. With OSC, it's an address-based protocol. So you can have different things listening on different addresses. So an address is like, it's like a Unix file path, like /alphanumeric/alphanumeric, and so on. So you can, for example, have like a certain value, like the cutoff of your filter, that could be like /filter/cutoff, and then that could expect like a floating point value, for example. And then the other end needs to know to send to that address and that data type. So as you might already be imagining, that creates a lot of flexibility, but it also means that there can be a lot of configuration required to make it work. So this is one reason it hasn't really caught on as much with musicians, at least not using it directly. Because if you want to have 2 pieces of software or hardware that use OSC as a communication protocol talk to each other, you need to set them both to use the same addresses for the same thing. So that's powerful, but it's also a lot of work to configure. In practice, one of the main ways musicians will use OSC is they will use something that uses OSC under the hood. Like they might use like a tablet app that they can use to control their DAW. And that might, under the hood, be using OSC as a communication protocol. But what it presents to them is just like a GUI, and both ends are made by the same programmer. So OSC ends up being a good way for programmers to have different pieces of software talk to each other. So yeah, I covered flexible address-based protocol, multiple data types. So each message in OSC, you can have an arbitrary number of values in it. And the values can be one of any number of different types. One of the types you can even do is like an array. So you can have like a bunch of values combined together. In my experience, most applications tend to just focus on floats. And oftentimes it'll just be like the message is one floating point value. So that's kind of the most compatible way to use it. It doesn't take full advantage of all of its power, but having a flexible address-based thing where you're sending floats, that's still very powerful and a lot more resolution than you get with MIDI. It's especially good for controlling parameters. It doesn't offer that much of an advantage in terms of keyboards, although you could do something like where you're transmitting the exact pitch that you want to play. So maybe the controller could support like microtonality and stuff like that. Or the controller could even be in charge of using different temperaments or whatever. And then OSC is designed to be transport independent. And in this context, transport means the means by which the messages are sent over. In music, you'll hear transport a lot referred to play, pause, and stuff like this, but that's not what I mean here. In this context, transport means the way that you're sending it. In my experience, most libs and most apps that you'll ever find just use UDP, User Datagram Protocol. And but Grig.OSC also supports TCP. And part of the reason is not all platforms, not all targets on the hack side have that implemented yet. Although in many cases I got around that by just directly using the native protocol, even though it wasn't in hacks per se. But UDP is like the main way. UDP has an advantage that it's very fast. There's like very little overhead. It does have the disadvantage that it's not as reliable as TCP, you know. There's a reason why HTTP and all that is based on TCP. But with UDP, you just want to send the packets quickly and receive them quickly. You don't want, you don't need to have like a lot of like error checking and stuff like that. So OSC is popular with open source audio devs. And this kind of goes back to what I said earlier about the importance of like the audio ecosystem. If you want hacks to be a good language for audio programming, you want to attract audio programmers, and open source audio programmers anyway, they like OSC. So it kind of, I think to me, I ended up prioritizing implementing this because it's like me signaling to them that, hey, this is a serious platform for writing audio code in, because now you can do OSC. So now with audio and MIDI and OSC, you can make a DAW, a synth, in theory anyway. Some limitations may apply still. And like with MIDI, OSC can be used for things other than audio and music. But because OSC is so flexible, it actually makes sense to do that, I think. So if you need like a test harness for a thing that you're making, so you need like two applications to send messages to each other, a good way to do that is OSC. You might want to look into Grig.OSC, and you can just have both ends use that and then just talk to each other that way. And that could be a good way to like, you know, change variables in a game engine or something. There's definitely lots of cool things about OSC. It often gets made fun of for being some pie in the sky thing that that regular musicians never really bought into, but it is pretty useful, I think, and it's definitely worth looking into. And here are the environments where I have it implemented so far. In Lua and PHP, I had to use its blocking. I use a blocking protocol because I don't have threads in those environments. But for all the other ones, you can do servers or clients in using OSC protocol. Well, and another thing that I didn't even add to this list, but it can be thought of as a client-server thing. So let's say like a sound module, something that just makes sounds and listens in on notes. That would be more like a server, something that listens in on OSC messages. A client is something that sends OSC messages. In a lot of cases, your thing is going to be both at the same time. But if you're only doing one or the other, it's like really simple. So let's move on. So you can see that I didn't even like intend on implementing Neko, but it kind of came for free because UDP is like already implemented there. And I even covered Hashlink. And I didn't give Hashlink any love on the audio and MIDI side yet, but it is supported for OSC. And like Java and C#, each of those only took me like a day or two to do, to add support for. So here is one interface for OSC clients. So you can see that's really simple. I instantiate a sender, and then I instantiate a client and pass in the sender to that. And then all I have to do from then on is just call client.sendMessage, and that sends the message up. There's also an example in the Grig repo that I mentioned earlier of sending MIDI over OSC. So one of the data types that OSC supports is actually a MIDI message. So you can actually have one computer connected to your MIDI keyboard, and another computer has like a synthesizer on it or connected to a hardware synthesizer, and send your MIDI messages over the network via OSC. So even without directly using OSC's own protocols, you could use it as a transport for delivering MIDI messages where they don't normally go. It's another way of doing MIDI over the network. But I'm kind of digressing here. So this is just a simple client code. Here is even simpler server code. So you just instantiate a listener, and then you pass that into a server, and then you just register a callback. And yeah, there's a more involved callback protocol that you can use where you actually specify which address you're listening on. But it's really simple. And with both client and server, if you don't want to use UDP or TCP and you want to make your own, like maybe you want to send it over RS-232 or something, all you have to do is just implement your own, implement the listener interface and implement the sender interface. Really, really simple. So in that respect, even if it's not a platform where I implemented any of the transport, the OSC semantics are automatically supported on all targets, on all HAX targets. So now I'll talk a little bit about the short-term future and the near-term future. And here is a stupid picture of flying cars, which we all know is never going to happen. So the short-term to do, the first one's going to happen really soon. I already have my Grig.audio rewrite working. It's just in the process of that, I was bothered by some of the interfaces and I changed them. And now I need to change a lot of other code before I can merge it back into main. But that should be done pretty soon. I might even work on that today and live stream it, but not making any promises. I'm busy with other stuff too, but I might do that today. And then I have a plan on going down and just like I did like a couple of weeks ago where I filled in the list of Grig.MIDI implementations, I'm going to try to do the same with Grig.audio and make as many quality functioning implementations as I can to bring, your hypothetical audio callback code to as many places as I'm able. And then so I recently, like maybe a couple of months ago, started a new website for Grig. So if you go to grig.tech, there's tutorials there. There's actually a lot of good information there. There's even a demo that runs in the browser and uses Hax React. So it's ultimately it's JavaScript code that's using React and the WebAudio and Web MIDI, but it's all made using Hax. And if you look at the source code for grig.tech, you can see how I implemented all that. But anyway, my plan is to add more tutorials there to hopefully make it easier to use. And then there's just some basic music stuff that's pretty easy to implement, that basically like finishing out grig.pitch and also probably making a grig.transport to support things like playback and stuff like that, and keeping track of the time and time signatures. In the long term is, I don't think I have time to talk about it today, unfortunately, but I started working, I did mention it briefly before, but I started working on my own Hax-based audio DSL that I call HXAL, Hax Audio Language. And that's actually coming along pretty well. And ultimately the plan with that is to make it so that inside of your Hax application, you can make your real-time audio code in that, and it should fit seamlessly with everything else. And then that way I can avoid having to deal with garbage collection in the audio callback. And then another use case would be to just make a class that uses that, and then from that being able to generate like native non-garbage collected code and code for different plugin formats. I did live stream some of my work on that earlier, so it might still be on my Twitch, some of the older stuff, but I'll talk about it more publicly when it's a little bit further along. Another thing is I made a controller script in JavaScript for Bitwig. I'd like to rewrite it in Hax. Bitwig supports JavaScript or Java controllers, so I might use the Java target and then rewrite it just to be another use case for Hax that's audio related, to contribute to that that ecosystem. And then ultimately I want to release something that I made using Hax instead of just working on the lib. And then ultimately I also want to release stuff in the target languages too, so that you have access to grig.audio in JavaScript and so on. So that's unfortunately I think I ran out of time. Are there any questions that anyone has?
Are we on? Hello? Yeah. Oh, yes. Yeah, you ran out of time like 10 minutes ago. So we'll just skip the questions for now.
Yeah, I'll answer them in the chat or something.
Yeah, exactly. Just indulge yourself. But I wanted to quickly ask you to also put into the chat the link to your stream where people can find you.
Oh, sure.
Because you were mentioning that you were live streaming. You were promising or threatening. I could tell.
Yeah, it is kind of a threat, yes.
You were promising threats. Also, by the way, I still have that little sticker of yours stuck in my car.
Oh, cool.
Of the little
Grig sticker.
Yeah. So cute.
So I'll drop the little fairy guy.
Yeah.
Okay, I'll drop that in the chat, and then I'll also drop it in the Discord as well.
Sure.
Okay, yeah, so anyway, thanks, everyone.
Yeah, thank you for the
very
talk.
Much.
We are going to take one final break for our last talk, so see you in 5.